In the second part of section 5.2, we're looking at perpendicular bisectors in a triangle. In class, we're going to do a discovery where we construct perpendicular bisectors in a triangle, or maybe you've already done it, but we're going to use a compass and actually do the construction. And we're going to look at what happens when you construct all three perpendicular bisectors of all three sides in a triangle. You're going to see some concurrent lines, important term that we're going to use a lot this chapter specifically. Concurrent lines are three or more lines that intersect at the same point. So three or more lines all intersecting at the exact same point. That would make these three lines concurrent. Again, it has to be three or more. And this point where they intersect is called the point of concurrency, because that's where those concurrent lines met. So concurrent lines are going to appear a lot this chapter. Three or more points intersecting, three or more lines intersecting the same point, and the point where they intersect is a point of concurrency. You're going to see a point of concurrency when you construct the perpendicular bisectors of a triangle. If you notice here, each of these lines is a perpendicular bisector of a certain side of that triangle. If I look at, let's say, this red segment, can you tell what side I perpendicularly bisected with the red segment? Well, it goes at a right angle with this bottom side. It's perpendicular here, and it bisected this side, so those are congruent. If you look at the green line, which side is it the perpendicular bisector of? Well, it definitely crosses at a right angle with this side AB, and so it also bisected this side. Oops, 2 tick marks. And finally, this blue line is a perpendicular bisector of this side BC, because it meets at a right angle, it's perpendicular, and it bisected or cut that side in half. And you notice all three of these perpendicular bisectors met at a very special point. They were all concurrent, and the point of concurrency is called the circumcenter. Now, what's special about this point? We have to think back to what we talked about and what happens when you have perpendicular bisectors from yesterday. The perpendicular bisectors, we notice, all intersect at the circumcenter, a point that is blank from the blank of the triangle. Well, let's think back to what we did previously with perpendicular bisectors. If this is a point on a perpendicular bisector, let's focus on the red one here. Remember how a point on the perpendicular bisector is equidistant to the endpoints of a segment. Therefore, this point is equidistant to the endpoints of the segment we perpendicularly bisect with the red, which is line segment AC. So, the distance from A to that point should be the same as the distance from C to that point. Those should be congruent segments. I'll mark it with I and V for 4. And think of it another way. What if I look at this point, the circumcenter, as being on the green perpendicular bisector? Now, this was a perpendicular bisector of side AB. It's a point on the perpendicular bisector of AB, therefore it's equidistant to A and to B. So this is also the same distance, and I can mark this with the IV again. All of these black segments are congruent. Now, where am I looking? I'm looking from the circumcenter to every vertex, and I'm noticing this circumcenter where the perpendicular bisectors meet. Seeing any point on the perpendicular bisector is equidistant to the endpoints of the segment. Here, the endpoints of the segments are the vertices of the triangle. So I notice that this circumcenter is equidistant from those vertices of the triangle. It's the same distance from the vertices, which is kind of awesome about the circumcenter. It's the same distance from every single vertex of that triangle. So, special properties of this point, the circumcenter, being the point of concurrency where the three perpendicular bisectors meet. We just talked about how it's equidistant from the vertices. If you notice here, I found the circumcenter again. The red lines are the what? The red lines are the perpendicular bisectors. The red lines are my perpendicular bisectors. They meet at the circumcenter. Those green lines show that it's equidistant to vertices. show that the circumcenter is equidistant to vertices. Those green lines would all be congruent. And finally, the coolest thing is seeing that the circumcenter is equidistant to the vertices. That means you could consider all of these green lines that are congruent the radii of a circle that hits every single vertex. Seeing those are congruent, we can draw a circle that hits every vertex. This circle is called the circumscribed circle, giving it the term circumcenter because it is the center of the circumscribed circle. Now the word circumscribed means that a shape is going on the outside of another shape and hitting all the vertices. Okay, so it's kind of cool. This green circle shows that, hey, I can do a circle, center at circumcenter, that hits every vertex, and I want to show you that this holds true in Geometry Sketchpad. Here I did the same deal. I constructed the perpendicular bisectors of the sides in red. I found the circumcenter where they intersected. I put segments in blue to every vertex. We know those blue segments are congruent. They also end up being the radius of that circle that hits every vertex. So I made a circle that hits vertices A, B, and C. I can change that triangle and notice that we still have a circle hitting every vertex. The cool thing is I can make the circumcenter go outside of the triangle. My triangle is ABC here. The circumcenter is outside of the triangle. That happens when you have an obtuse triangle. I can make a right angle, and the circumcenter is right on the triangle here. And I'm able to kind of manipulate this even more. So the circumcenter is a very cool point. It's the center of the circumscribed circle. It's the one that touches every vertex. And get rid of that. And this is the circumscribed circle. So if you have trouble remembering circumcenter, think, oh, it's equidistant to the vertices, so I can do a circle that touches the vertices. And that circle is outside of the triangle, so it is circumscribed. Therefore, it's the circumcenter. Okay. On this next slide, I just am pointing out we did have the location of the circumcenter varying. In any acute triangle, that circumcenter will be located somewhere inside the triangle. In any right triangle, the circumcenter is on actually the hypotenuse. Of that right triangle, so it'll be opposite from that right angle. And this is, of course, the midpoint of that hypotenuse because it is a bisector, perpendicular bisector. In an obtuse triangle, it is outside the circle. Oh, outside the triangle, sorry. The circumcenter will be located somewhere outside. And I'll just write inside the triangle for acute. And let's see here. I'm going to actually do the circles. If I go to my shape tool and I do my circle, this circle allows me to start at the center, which I know would be the circumcenter. If I go from here, create a circle, it should touch every vertex. There we go. From the circumcenter, if I go to any vertex, I should touch all three vertices. And I am. And from that circumcenter, should go out and touch every vertex. And once again, I am. So the circumcenter location can change relative to that circle. In an example here, which is kind of neat, if you were, in this case, going camping, it looks like, and it says you want to choose the campsite that's closest to the lake, the bathrooms, and the firewood. All important locations that you're going to need to get to at some point while you're camping. And you want to find where in here am I going to go so that I would be the same distance from all three of these. Well, how could you find that point? What would that point be called? You're thinking about it. You want a point that's the same distance from three different locations. I need you to come up with a plan for this because we're going to do this in class tomorrow. This is your homework. Give me a plan. How are we going to find the location that will be the same distance from all three of these things? And a little bit more before we're done with this video here. We see a triangle. It tells me that point C is the circumcenter of the triangle. C is the circumcenter. That means that perpendicular bisectors must have met at C. Okay. So if this is the circumcenter, we know that perpendicular bisectors met there. Met at C, that was the point of concurrency that found the circumcenter. It was created by the perpendicular bisectors. Where are the perpendicular bisectors in this picture? It must be, this looks like a perpendicular bisector. That goes to a vertex. This, though, is another perpendicular bisector. 2 tick marks there. Goes to a vertex, this is a perpendicular bisector of this side. Okay, I'm just going to get rid of all these in case I don't need them. But we know where the perpendicular bisectors are. Well, what's great about the circumcenter? We know the circumcenter is equidistant to the vertices. Because again, if I think of like this perpendicular bisector, C should be equidistant to Y and Z. If I think of this perpendicular bisector, if C is on that, it should be equidistant to X and Z, so that gets 1 tick mark. And similarly, if this is a perpendicular bisector, C is equidistant to X and Y. So all of these should be the same length. This should help me finding CZ and CX. Let's check it out. CZ. C to Z, that has to be equidistant to all of these, CX and CY. If CY is 10, distance from the circumcenter to a vertex should be the same to any vertex. So C to Z is also 10. And C to X, again, circumcenter to vertex, also 10. These are equidistant. I could grab that circle tool again and create a circle that would hit all 3 vertices. So properties of circumcenter today, learning about what makes this point special. When you do the perpendicular bisectors in a triangle, they will meet at that circumcenter.